Hi, and welcome to this video where I'm going to teach you how to take a point cloud or a list of order points and see if there are any duplicate points on that list and remove them, or if the points are below a particular threshold or a particular tolerance. If they're very close to each other, then also to take them, to remove them from that list, okay? I'm going to be implementing this in C#. I'm going to be using Rhino and Grasshopper, which is a visual modeling environment. But all the code that I'm going to be writing is pure C#. So if you're interested in this, you will find that the logic and the algorithms are very easy to translate to other environments such as Python, JavaScript, etc., etc. I'm also going to be breaking down exactly what are we doing and what principles we're basing ourselves on. And I will also be discussing a little bit of how to optimize this process so that it's a bit less computationally intensive. And finally, I would like to say that the process that we're going to follow works for point clouds. But if you want to compare, line segments and or if you want to compare vectors, this algorithm can also help you figure that out. Okay, so without that, let's get started. Okay, the first thing that I would like to explain is that I have created this small visual algorithm that creates 50 or however many points randomly in three-dimensional space and then duplicates and triplicates some of them. Okay, so right now what I have is a list of 65 points, 50 of which are the original ones, so you can see them here, all of them are original, and then 10 of them have been duplicated. You can see them in green, and then 5 of them have been triplicated. Okay, and I can control that numerically with these sliders here. How many of them more or less are duplicated and triplicated? If you're interested in knowing how I did this, just check the original recording, and a link to that should be here in the description of this video. Okay, and last but not least, I've joined all those lists and I have randomized them to make sure that where those points, where those duplicate and triplicate points are on the list is always going to be randomized. Okay, this gives me a list of random points with some of them duplicate and some of them triplicate, which now I'm ready to start writing an algorithm to be able to clean them up. Okay, so let's get to that. Great. So here in Grasshopper, which is what I'm using to implement this algorithm, I'm using Grasshopper and Rhino because it allows me to write things in, it allows me to write scripts in C# scripting. It has a geometry kernel that then I can use for visualization purposes. So it's very visual and it's really easy to see if things are working well or not. Okay. Now, what I'm going to do here is I'm going to drop a C# script component. This C# component is going to take the list of points here. So I'm going to rename the inputs and I'm going to call it points, for example. Very eloquent, right? And then I'm going to make sure to right click on the input and make sure that I forcefully cast all these objects to be in 0.3D objects so that I can access their X, Y, and Z properties. This is because I'm using the Rhino common library, geometry library, but if you don't have this, then in your function you can just input like a list of some class or some struct that you're using to represent those points, okay? And then also here in the C# script component in the input, I'm going to make sure that I change the input type to be list access instead of item access. Because if I leave it as item, then the component is going to run 65 times, one for each one of the points that I have. Whereas what I want is I want the component to run once with the full list of points so that I can compare them between them. So I'm going to do that. And as I do that, now I can double click on the component and you can see that my main function, that one that runs inside the component, has an argument that is the list of 0.3D objects that is coming into the component, and then the output is going to be this a ref object, which I'm actually going to rename. I'm going to rename to clean points or something like that. Okay, and then you see that renames the output here, and then now I am ready here to start writing my algorithm. Okay, so let's start doing that. The first thing that we're going to do is we're going to create a super basic algorithm to get things running, and then what I'm going to do is I'm going to check just the first point of the list, and I'm going to check it against all the other points on the list and see if it can find any duplicate. And in order to do that, I've actually changed the algorithm a little bit, and I have temporarily deactivated the randomization, because I want to make sure that the first point has some duplicates that we can test again. And if you remember here, you remember that the first point is triplicated. So this point, which is right now on position 0, is duplicated on position 5, and it's also duplicated in position 15 here. So that we want to verify that our algorithm can detect duplicates. So that's why I have deactivated right now randomization, and we know that the first point has 2 duplicates on the list. So let's start very simple. What we're going to do is we're going to write a for loop where I'm going to go over all the points. I'm going to go over all the points in my list. So points dot count I++, and then I'm going to close this parenthesis. Then I'm going to take here point 3D. I'm going to take the first point, and this is going to be from points. I'm going to take the first one, and then here I'm going to write some code to compare with all the other points. Okay. And what is that going to be? And this is what I wanted to get. The first thing that I would like to do is I would like to compare the first point with all the other points. And how can I compare 2 points to see if they're duplicate? You might be tempted to do some kind of rule where you take the first point and then you say, is the x coordinate, that number, equal to the x coordinate of the other point? And is the y coordinate also equal to the y coordinate of the other point? And is the c coordinate of my point equal to the c coordinate of the other point? And if the 3 points, and if the 3 values are equal, then it means that the point is duplicate. That is an okay intuition, and we're actually going to implement that rule right now. But I want to do that to prove that it's actually not a good practice. It's actually a pretty bad practice to do that for the reasons that I will explain. So let me show how that would work. I'm going to write here a comparison, and this is going to be I'm going to create a function that compares the 2 points numerically in that way that I have described. So the return value is going to be true or false, and my function is going to be called are numerically equal. It's going to take a point 3D called A, another point 3D called B, and then what I'm going to do is I'm going to say I'm going to return here equal. I'm going to create a variable called equal, which is going to be the expression is A, the x coordinate of A, equal to the x coordinate of B, and this is a fairly common way of and is the y coordinate of A equal to the y coordinate of B, and where is the end? And is the c coordinate of A equal to the c coordinate of B? So this should be a Boolean value that is this and this and this, and which is what I'm going to return with this function. And now here, what I can do is I can say if r numerically equal, if these points are numerically equal, I'm going to do a variable here, and I'm just going to say are numerically equal the first point and the point that I'm comparing against right now. And if they are equal, then just print a message to the console. Print point 0 is equal, point 0 is equal to point I. Okay, I'm going to run this code, and int I, I'm missing this here, and then actually this is working. Okay, um, but this is working because I have probably generated all the points inside of C sharp, and they have like they're all coming from the same instances of the same structure, and like their precision is the same. But doing this is actually not a good practice at all. Okay, and the reason why this is not a good practice is um, because because numbers with decimal part in any programming language that I can think of, they have a limited precision. They're not, we cannot think of them as exactly precise decimal values because the way they are stored in memory means that they actually have some inherent imprecision to the value that they're storing, and this is very easy to see. If we do, for example, this exercise where let me create a Boolean variable that I'm going to call sample. And here what I'm going to do is I'm going to say, if I multiply 0.1 times 0.1, what is the value that I should get numerically? Numerically, I should get 0.01, right? So let me see if comparing that multiplication to the actual value of 0.01, let me see if this value is true. And let me print that here. Print uh, sample number comparison is going to be equal to sample. Okay? If I run this code, you can see that sample number comparison is equal to false, which means that this expression, which numerically is equal to 0.01, is actually, the computer cannot see it as equal to 0.01 because internally, very likely, the first number is something, because 0.01 in a computer internally, due to the reasons of floating point precision, blah, 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 is probably something closer to something, 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 and then a bunch of numbers like this. And if I multiply two of those, then 0.1 times 0.1 is probably equal to something that looks something like this, and a bunch of zeros, and now some other numbers here. And what happens is that if I store this number without coming from the multiplication, then it probably looks something like this, with also a bunch of zeros, but what's trailing behind, it's different. And the computer gets lost in this kind of precision that we have here. And therefore, when we compare this value, so these two multiplied, which more or less for the computer is this one, when we compare with this one, you can see that this very, very small imprecision is what's triggering this equality to be false. This is not a bug in the programming language. This is not something that is wrong with the programming language. It's just part of the limitations that are inherent to the fact that we need to store numbers with precision values in zeros and ones inside of a computer. Okay, so this is something that is actually very normal, and that's why when you compare numbers, you're actually very, very discouraged, especially if there are numbers with decimal precision. You're very discouraged of comparing them with equality sign, like we've done here. If you're comparing integers, you're fine. But decimal numbers, they do have this limitation. So it's not a good system to compare them like this. So we need to find a different way of figuring out if the point is duplicate or not. So let me explain how to do that. So in order to make a better comparison or a better way of finding duplicates, what we need to understand is that if we have like a random cloud of points like this one, and we want to see if, for example, this point has any duplicates, then a better way of approaching that problem is to think of equality of points as measuring the distance between the point that we're checking and any other point that we want to check for duplicates. So if I think of this point and I was able to calculate the distance between this point and any other point, the closer that distance is to 0, then the more assured that I am that that point has a duplicate. So if we think of this second point here as like being very, very, very close to that point, then it just so happens that if we calculate this distance and that distance is 0, then that would mean that that point is duplicate. But we still have the same problem that I just has described before. We can't really say, I'm going to calculate the distance, and if that distance equals 0, then that point is duplicate. Because again, we can just not take numbers and compare to other numbers by means of equality. So actually, what's usually done in these cases is that what we do is we don't try to find points that have a distance of 0 to other points. What we do is we try to find points whose distance to the duplicate is below a certain threshold, is below a certain number that we set as the precision for our comparison. So for example, if we say that this value should be less, that distance should be less than 0.00000001, then that we can probably be assured that they're so close that we can practically say that they're identical. Okay, and that numerically works much better than the system that we were using before of comparing values for equality. So the rule that we're going to implement is just going to be super easy. We're going to check every point. We're going to calculate the distance of every point to any other point on the list. And then if that distance is below a particular threshold, a particular number, then we will consider that those 2 points are duplicate and we will remove one of them from the list. That's it. That's what we're going to do. So let's see how that works numerically and code-wise. Let's get it done. Great. So in my previous geometry gem, I explained how to calculate the distance between 2 points numerically. So I created this function that given 2 points calculates the distance and return that. So if you want to learn more about why and how this was implemented, please make sure to check that geometry gem. Probably there might be a link somewhere to it popping here. That was geometry gem 4. And then what I'm going to do here is I'm going to calculate the distance. So for example, I'm going to say double D is going to be equal to distance between the point that I'm checking, the first one, and then, sorry, that's going to be first, and then points, each one of the points that I'm calculating, all right? And if that distance D is less than a very small value, so for example, this one, then I'm going to print here the value. 0.0 is duplicate with point I. And then I'm going to run this code, see if it works, and yoo-hoo, it's working. So we can see that 0.0 is duplicate with itself, so that's a good sign that the calculation is working, and it's also duplicate with 5 and with 15. I think we're good on track. However, I don't tend to like this hard coding numbers inside of algorithms. I like things to be as programmatic and controllable as possible. So I would like this to be something that I can control externally. So what I'm going to do for that is I'm going to implement another input on my function. I'm going to call this tolerance or threshold or however you want to call it. I'm going to make sure that this is something of the type double. And then I'm going to plug in here a very small value. So for example, 0.01. Okay. And then that is what I'm going to use in my algorithm for calculations. So tolerance. Okay. I'm going to run this code and it looks like it's working. Okay. So that's cool. So we're on good track. So the only thing that we need to do now is we need to write something where we go over all the points and then we start removing them one at a time. So let's take care of that. Okay, I've cleaned everything up because we're going to start from scratch. And the way we're going to implement this is that first we're going to write a for loop where we're going to go over each one of the points one at a time. And then we're going to compare that point with all the other ones on the list. So that's going to be a for loop int I equals 0. I is less than how many points do we have on the list, and then I plus plus. And then that is our large for loop. So this is the one, go over each point on the list. And then here, we want to compare with the rest of the points. So for this one, I'm going to write another for loop where I'm going to say int j equals I, because this I plus 1. And I will explain in a second why points dot count and then j plus plus and then here. And let me actually draw a diagram of why this second for loop, it starts at I plus 1. Let me do a diagram here. What's important to keep in mind here is that we want to be we want to make our code a bit more optimized, because since we're going to be comparing a lot of things back and forth, if we don't control this well, then the amount of calculations that we do can grow exponentially very fast, and many of them being unnecessary. Because like, think about this: if we have all of our points in a list, for example, say we have 10 points. They're a list of order points. And what we want to do is we want to compare it between each other. Then what we probably want to do is we probably want to start with the first one, 0, right? And then we want to compare this one, 0, to the other, to the other 9, right? So the second for loop that we want to start, we probably don't want to start it at 0, because if we do that, then we're going to end up comparing this value to itself. So what we want to do is we want to start the second for loop with the value of 1 and going all the way to 9. If we are, for example, somewhere in the middle, let's say, for example, we are on item number 3. If we are in item number 3, it means that we've already compared number 0 to number 3, number 1 to number 3, and number 2 to number 3. So what we want to do is we want to do the rest of the comparisons that are available, which is 3 with 4, 3 with 5, 3 with 6, 3 with 7. And so what we need to do is the second for loop needs to start and needs to start with number 4 and only go all the way to 9. So that's why if I equals 3, the first number that we want to check in our j loop is 4. Sorry, it's going to be 4, which is going to be equal to I plus 1. Is that clear? So basically what we're doing is we're comparing all these points in a sort of triangle way, because we're always comparing the first one with all the rest, then the second one with the rest, the third one with the rest, the fourth one with the rest, etc., etc. All right, so let's get back to the code. So if we go back here, now you can see that our for loop, the second for loop is going to start with j starting with whichever index number we are plus 1, okay? And then here we can start comparing. We can say double D is going to be equal to the distance between points I, so the original point that I'm comparing, and points J, the second point that I'm comparing in this operation. And if D is less than tolerance, then let's print a message just to make sure. So I is duplicate of J. Is that going to work? Let me see. 60. Where is lines? What have I done wrong? Yeah, so J is less than, okay. All right, so let's see. 0 is duplicate of 5, but this time we're not finding that 0 is duplicate of 0. 0 is duplicate of 5 and 15. 1 is duplicate of 6 and 16. Oh, this makes a lot of sense, especially because I didn't shuffle the list. 5 is duplicate of 15, 6 of 16, 6 is it. So this looks very well to me. This is very good to me. So I guess, and you see there's also something interesting. 0 is duplicate of 5 and 0 is duplicate of 15, but also 5 is a duplicate of 15. So these two are also found here on this list. So that's great. So I think we are off to a good start. And now the only thing that we need to do is we need to make sure that when we find a duplicate, we remove that duplicate from the list. Okay? Let's see how we would do that. Very easy. The only thing that we need to do is that now that we know which one is the index number of the point that we need to remove from the list, then it's just as easy as saying go to the points list and then remove at, and then just remove whichever item is at position J. If I do that, I'm going to run this code and I'm going to see that clean points now has 50 elements, and remember that that is correct because we generated 50 random points and we duplicated and triplicated some of them. So we ended up with 65, but the original points should be 50. So that could work, or it looks like it's working, but that's actually not the case. And I can prove it to you if we now randomize the list. So remember that we were working with the list that was not randomized. If we now randomize the list, it may so happen that that depending on how the list is randomized, you see that now the output, instead of being 50 points, there are 51. That means that one of them has somehow skipped the check and has gone through without. And if I actually crank up the duplicate list to for example 50, so now we should have 105 points. I'm sure that this, you see, it's still 51. It's not doing the job correctly. So why is that? Let me explain that back with the diagram. Imagine we are here, and we are checking this point against all the other points. So the index number here right now is 3. And then we start checking points. But let's see what happens here. Imagine these 2 points, this one and this one, are actual duplicates of number 3. Whenever we hit J and we make it 6, all right, we find a duplicate, and at that point we remove from the list whichever element is number 6. Okay, so we remove this element goes away, but then as we do that, something happens. And what happens is that the rest of the elements that are left on the list, they reorder, and these values, these index numbers now change, and this becomes 6, this becomes 7, and this becomes 8. You see what the problem is now? Because we are on a second for loop, now the value of J increases to J equals 7, which means that on the next iteration, the point that we're checking against is not this one anymore, which is the real duplicate that we want to find, but it's this one. So the next point that we check is this one here. And what that means is that we have actually skipped checking number 3 against one value, which means that there are situations where if 2 points that are duplicate and are consecutive with each other, if we iterate this way, frontwise, then we may actually jump over doing checks on some particular points. And indeed, we will always, whenever we find a duplicate and we remove that duplicate, we will always skip checking the next point after that. And that is not great practice. So how can we solve that? The fix to solving this is actually pretty easy. And let me show you, where is my mouse. Let me show you how to fix this. The fix to doing that is actually very easy. And the only thing that we need to do is, let's say we're here and we are at I number 3. The only thing that we need to do is, instead of iterating with our second for loop this way, so with j starting at 4 and then doing 5, 6, 7, so what we need to do is we need to flip the direction in which we check the second for loop, and we need to check all the elements this way, with j starting at 9 and going back to 8, 7, etc., etc., etc. Because see what would happen. Imagine we have these 2 points, imagine this point and these points are duplicates of number 3. If we iterate from the end to the beginning, we may find that this point, number 7, is a duplicate, so we remove it. And then what happens is that the rest of the elements on the list, they get renumbered. So 8 and 9 becomes 7 and 8. But we don't care about that because we were at J7 and we removed element on position 7. So if we now go to J6, this number has not been affected by removing the element from the list, and therefore we're not going to skip any element. So that's why when you are, in general, when you are iterating over a list of elements in which you intend to remove some of them based on some condition, then it's always very advisable to iterate backwards, iterate from the end of the list to the beginning of the list. So let's see how we would do that with the code. And remember that right now the code is not working because it's giving us 51 elements. So let's go back, and now let's just rewrite this so that loop backwards to make sure we don't skip any item. All right. So what I'm going to do is I'm going to start my for loop at whatever point dot count -1 is, because if we have 10 elements, we need to start by element number 9. Now j will always have to be greater than I. So if we go back to the diagram, if I start with j, j is always going to have to be greater than I. So the last number that we want to check is number 4. And I and j is going to go backwards. So it's going to start from the end to the beginning. And the rest of it is the same. So let's see if I run this code. No, j has to be greater, greater than I. If I run this code, you can see that now I have 50 elements, and that the order of my checks has changed a little bit. 4 is a duplicate of 18, but now of 9, 6, etc., etc. So my code is now much more resilient. It's better written. Okay. So remember, this is a really good advice. Whenever you loop over a list in which you're going to be removing elements, always loop backwards. Okay. So that's it. We have implemented the algorithm. However, I want to recommend a small optimization. Okay, and that optimization is related to the fact that we are calculating distances between points in order to decide whether if we remove those points or not. And calculating the distance involves using the square root of a number, which in computational terms is an operation that is slightly more costly than just simple additions and simple multiplications. So let me show you a trick to make this. So if we were just calculating this for 100 points, maybe it doesn't really make a difference. But if we were doing this for a large point cloud of millions of points, then we would really need that optimization. So let me show you a trick of how can we optimize this and make it a bit faster. Okay. The key to understanding the optimization that we're going to do is to understand that, in fact, we actually don't really care about the real distance between the 2 points, because what we care about is comparing that distance to a particular value that we are comparing against, and if that's greater or smaller, then we make decisions. So if what we want to do is we want to save ourselves a little bit of calculation, then instead of calculating the pure distance, which involves a square root, and then comparing it to the tolerance value, so if instead of doing distance is smaller than the tolerance value, if we can also understand that if this works, if distance is smaller than the tolerance value, then just numerically, the square distance, so, wow, that was terrible. So d squared is also going to be equal to tolerance square. It's going to be less than tolerance square. If I square both values, then both values are still going to be, one is still going to be less than the other one, which is what we are interested about. We don't really care about the value of the distance. We care about comparing it with the tolerance. So if what we do is we compare, instead of the real distance that needs a square root, we compare the square distance, which doesn't need a square root, and is much faster. If we compare that to tolerance square, then our code is going to run much, much faster. So that is the core of the optimization that we're going to do. I have written here, I have pasted from my previous geometry jam, I have pasted a function that calculates the squared distance between 2 points, which is basically the distance, but without the square root part. So it's just exactly the same. So what we're going to do here is we're going to first calculate a value of, I'm going to call this T2, and this is going to be tolerance times tolerance. And then here I'm going to, actually, wait, sorry. I'm going to save this component, okay? And then I'm going to copy and paste a copy of this somewhere where I'm going to, I want to compare normal distance to square distance. Here I'm going to do double T2 is going to be tolerance times tolerance. And then here I'm going to compare D2 is going to be, instead of distance, is going to be distance squared. And then if D2 is smaller than T2, then figure out if it's duplicate or not. I'm going to run this code. I'm going to output this here. You can see that the two outputs are identical, which means that the algorithm works the same whether if I use regular distance or square distance. Now, does it run really that much faster? Let me try. Can we crank up the value of how many points do we have? So if instead of 50, if I do here 1000, can we actually, oh, let me turn on the profiler. Oh, actually that was very, very fast. So let me actually, can we crank this up to 1 million? And let's hope that I don't crash my computer. Let's do 100,000 first. So let's see if what happens. I'm going to save this. Let's see what happens. If I do that, you can already see that my computer has frozen because this calculation is taking some time and still not responsive. And 100,000 element, it's literally, it's nothing for a cloud point. A cloud point is usually millions. Oh, it's usually millions, if not like in the billions. I'm still frozen. All right, sorry, but my computer froze and everything crashed because 1 million was definitely too much. So I lowered the count to 10,000, and I also disabled a lot of visualization and a lot of the console printing. And it also happens that we have a little bit of a bottleneck with the component that I'm using to populate, to generate the random points. So we could have done that manually. We could have done, maybe we can do that like a C# component that just populates random values. This one takes 22 seconds to compute, but it gives me 10,000 points. And then when I duplicate them and etc., I get 10,015 points. Now, after cleaning them up, I get the 10,000 points, but you can see that by changing from square root to not square root, I have gained roughly, what is this, 15% in performance. So depending on what I'm doing, this is actually quite a big deal in computational terms. So bottom line, when you want to compare distances between points, when you want to compare lengths of lines, when you want to compare lengths of vectors, you're much better off using the square distance or the square length. You will see that in the literature a lot as well, as opposed to just using the straight distance or the straight length. Okay, so that was it, I think, on my end. As I said, this algorithm is also very helpful if you want to compare lengths of segment distances or segment of line segments or length of vectors. Yep, and I think that's about it. Thank you very much. Oh, I totally forgot to mention. This algorithm that we just wrote is also very useful if instead of looking just exactly for duplicates, if you also want to call or you want to remove from the list points that are very close to each other. Because remember, we have used the tolerance approach. So we can just choose like a very, very small number to approximate for points that are exactly identical. Or if we just increase that number, we can also just clean up points that are reasonably close to each other with a certain tolerance. So for example, what you see here is a box where I have 1,000 random points. 15 of them are duplicate, but and this box is 2 by 2 in diameter, in size. So these are the clean points, but if I actually start increasing the tolerance, you can see how points that are near to each other start disappearing. So this can also be a way of cleaning up a point cloud and leaving it in a way that the points are sort of at a certain distance, at a minimum, at a certain distance between each other. So it could help, for example, if you have a mesh and you want to do like a mesh simplification. It doesn't really work like that, but it could be a start of doing that. Or if you want to just get like a sample of the points that are more meaningful, this could also help you do that. Okay, so yep,